trigonometric functions. If we have to identify or understand trigonometric functions, the first thing that we have to understand would be the coordinate system. We all know the real number line, the xy axis. And for instance, we could draw a line here or a curve, so maybe a parabola, and that is drawn on a Cartesian plane or a rectangular coordinate system, in the sense for each value of x we end up having a value of y. But if we want to bring the sine and cosine functions onto the rectangular coordinate system, it is best that we understand the polar coordinate system. So to that end, we need to consider the unit circle, and every point on this unit circle can be related to the rectangular system. So I'm going to make a connection between the polar coordinate system right here to rectangular, and as I move along the unit circle, I'm going to generate the sine function, which is y equals sine of x, and the cosine function, y equals cosine of x. So a key thing to note in a polar coordinate system is the angle theta. So what do I mean by that? If I draw a line that way, that particular line has an angle with respect to the axis being the x-axis, so we would have an angle of theta. So what we're trying to say is that the line that I drew is at an angle of theta from the x-axis. So the point here on the unit circle can be defined using that particular angle. First off, what do I mean by a unit circle? A unit circle is simply a circle with radius 1. So how do we come about, or how do we come up with these 2 points, that particular coordinate in red in the polar system? What we can do is make use of the Pythagorean theorem. So I'm going to draw a vertical line there. So now I have a right-angled triangle. So I'm going to take that right-angled triangle and I'm going to draw it over here. So that is the point that we're looking for, and that is the angle theta. So what do we know about a right-angled triangle? It has 3 sides: the hypotenuse, the opposite side, and the adjacent side. Now, why do we call it the opposite side? The side is opposing the angle theta. So from the perspective of theta, the side, the the side is opposite to theta, so we call it the opposite side. The adjacent side is called the adjacent side because it's right next to theta. And of course, the hypotenuse is how it was defined then in the Pythagorean theorem. So, in the polar coordinate system, the sine of the angle is simply the opposite side's length divided by the hypotenuse. So, if you look at this picture in the unit circle, the vertical line is of length y and the horizontal line is some arbitrary x. So if I call it length y and x, then that point would simply be x comma y. So I can come back here to sine theta and write the opposite side, which has a length of y, divided by the hypotenuse. The hypotenuse here is simply the radius of the circle, which would be right there, and it is of length 1. So I have related the coordinate y to sine theta in terms of the angle. In a similar manner, if I take cosine theta is simply the adjacent side length divided by the hypotenuse. The length that I defined for the adjacent side is x. The length of the hypotenuse is 1, which would simply mean x is equal to cosine theta. So the coordinate right here in the rectangular form is equal to cosine theta and sine theta in the polar form. So we made a connection between the real number line and the polar system that we have. So oftentimes we don't like to use the same notation x and y with the polar system. Rather, we call it r and theta, so the radius axis and the angular axis. So that is not of importance in this case. Now, to complete one full revolution about a circle, we need to have 360 degrees. So if someone said, oh, I went around a roundabout, then you actually covered 360 degrees. So we start with 0 here, and the next part, the vertical part, would be 90-degree angle, and 90 degrees can also be written as pi over 2. That would be the radian measure. So pi is simply 180 degrees. So a radian measure of pi would equal to an angular measure of 180 degrees. So that's radian, and that's the angle. So the angular measure is used in the polar coordinate system. The radian measure is used in the rectangular coordinate system. So 90 degrees would correspond to pi over 2, and then 180 degrees would correspond to pi. Add another 90, we'd have 270 degrees, which would be 3 pi over 2. Add another 90 degrees, you would end up getting 360 degrees. So, which is equal to 2 pi. So 0 and 2 pi would pretty much be one and the same when it comes to the polar coordinate system. So if we went another full revolution, we would sweep another 2 pi, so we would have a total radian measure of 4 pi. So how do we make the connection between this system, which is polar, and the rectangular system to explain the sine function and the cosine function. If you look at the graph over here, we have sine of 0 to be 0. So if the angle is 0, what is the value of sine? Well, that's the origin. We have 0, x to be 0, so 0, 0 would simply be 0. Now, if the angle moves upward toward 90 degrees, in the sense moving that line, the hypotenuse, from 0 all the way to 90 degrees, when I do that, what is the corresponding value of y? You may ask me, well, why are you looking at the value of y? We're looking at the value of y because we have made the connection that y is equal to sine theta. So as I move from theta equals 0 to theta equals pi over 2, which is 90 degrees, what is the value of y? So when that particular line moves right over here, that length ends up being 1. So at pi over 2, we have a value of 1. And as we move from an angle of 90 degrees down to 180 degrees, in other words, I'm moving the hypotenuse toward 90, then back to 180, and it would come right over here. And what is the value of y on the x-axis? It would be 0. So at pi, we get a value of 0. And as we move from pi to 3 pi over 2, the line comes right over there, and naturally that is of radius 1, but on the real number line it would be negative 1. So here we would end up having a value of negative 1 at 3 pi over 2. 270 degrees is 3 pi over 2. And back to 0, I'll have a length of 0, which is right over here. So when I complete one full revolution in the polar system, I actually trace that part of a sine wave. So you can see the period of a sine wave is 2 pi. Sine wave or sine function. So when you repeat this and go for this next revolution about the circle, the wave or the function is just going to repeat itself time and time again. So whatever you see at sine pi over 2 will be the same at pi over 2 plus 2 pi. So since the period is 2 pi, if I pick sine pi over 2 and add 2 pi to it, I will simply get the value of sine pi over 2 because the period is 2 pi. The same applies on the negative side. If I did pi over 2 minus 2 pi, that would also give me a similar answer. So what do we know about sine pi over 2? Sine pi over 2 is 1. And sine pi over 2 plus 2 pi is sine 5 pi over 2. So we pretty much end up saying that sine 5 pi divided by 2 is 1. Is that correct? So 5 pi over 2 is right over here. And as you can clearly see, that corresponds to a value of 1. So that's just the sine function. Now, the cosine function can be derived in the exact same manner. only this time we know that the cosine of theta is related to the x-coordinate. So what is the value of the x-coordinate when the angle is 0? When the angle is 0, the value of the x-coordinate is right here, and that value was 1 in the polar system. So in the rectangular system, an angle of 0 would correspond to a value of 1. Now, if I move and do one full move to 90 degrees, then I would come to that point, and we know that the value of x in the rectangular system would equal to cosine theta in the polar system. And you can see in the unit circle, since we are on the y-axis, the value of x would be 0. So cosine pi over 2 is 0. And as I move here, I'm still looking at the x-coordinate, because the x-coordinate would correspond to sine theta. So that would correspond to the length on the x-axis. And what is the value of x on the x-axis on the left-hand side? It is right over here. Whoa. Messed it all up. Didn't expect that to happen. Okay, more or less it works. So that length here would be -1, because we are looking at the left hand side here. So at pi we have -1. Just like the sine function, the cosine function would also have a period of 2 pi. So let's say the value of x is 0. So if x is 0, then y equals cosine of 0 must equal 1. That's what we established in that graph. So if I add 2 pi to it, cosine x plus 2 pi would equal cosine 0 plus 2 pi, and that would give me cosine of 2 pi. And since the period is 2 pi, whatever value that we saw at 0 would also appear at 2 pi. So cosine of 2 pi must be 1. Is that the case? Well, if we come back here, we can see that cosine of 2 pi is 1. So key things to note about sine and cosine functions is that they are directly related to the unit circle, and they have a period of 2 pi. So by all means, we just have to know the values of sine and cosine between 0 and 2 pi. If we know those values, then we can extend that to any radian measure simply by adding 2 pi and finding the corresponding value of the function. Here comes the next function, which is a tangent function. We know that tangent of theta is simply the opposite side divided by the adjacent side, or the length of those sides. So opposite divided by adjacent, which in my diagram over here, I call that length to be x and y. So pretty much tangent of theta would be equal to the value x divided by y. But we know we made the connection between x and theta. X would be equal to cosine of theta, and y would equal sine of theta. So x divided by y is simply equal to sine theta over cosine theta. So a tangent function is simply sine x divided by cosine x in the rectangular coordinate system. So we know that cosine will become 0 at pi over 2, 3 pi over 2, 5 pi over 2, and so forth. In other words, the denominator is going to become 0 in a tangent function. So anytime cosine becomes 0, then we have a problem because we are going to divide the sine function by 0. So cosine of x and so on. So cosine of x becomes 0 at plus or minus pi over 2, plus or minus 3 pi over 2, and so forth. In other words, at those values, pi over 2 and 3 pi over 2, denominator would become 0, and we would end up having a vertical asymptote. So the dotted line that we see here is the vertical asymptote. Now, if we look at the sine and cosine functions, they repeated the function repeated itself with a period of 2 pi. So whatever we saw between 0 and 2 pi will happen between 2 pi and 4 pi. Whatever that we see between 2 pi and 4 pi would be the same that we would see between 4 pi and 6 pi. That said, if we come back and look at a tangent function, whatever that I see between negative pi over 2 and pi over 2, right here, is what I see between pi over 2 and 3 pi over 2, and it is the same that I see between negative 3 pi over 2 and negative pi over 2. So the point I'm trying to make here is that the period of a tangent function is pi, in the sense for any x tangent of x plus pi would simply equal to tangent of x. So there are some identities that are very crucial when we deal with trigonometric functions, and oftentimes they come into play when we try to differentiate or integrate. So let me start with the product to sum identity, and we can go back to sum to product after doing product to sum. So By definition, sine A plus B is simply sine A times sine B plus cosine A. Oh, sorry. Sine A cosine B plus cosine A sine B. That is by definition. So instead of A plus B, if I have A minus B, we would simply have sine A cosine B minus cosine A sine B. In a similar manner, cosine A plus B is cosine A cosine B minus sine A sine B. So instead of A plus B, if I have A minus B, then the identity is cosine A cosine B plus sine A sine B. So I'm going to derive one of the product of some identities, and if we use the same process, we can come up with every single identity. We have 4 of them. So I'm going to start with the case So by definition, sine A plus B is sine A cosine B plus cosine A times sine B. So sine A minus B would simply equal to sine A cosine B minus cosine A sine B. Now, if I add these two equations, I would have sine A plus B plus sine A minus B equals. So the term on the far right would get cancelled. And I have sine A cosine B, sine A cosine B. I'm adding it, or adding them, so I would simply have 2 times sine A cosine B, which would mean sine A cosine B would equal to 1 over 2 sine A plus B plus sine A minus B. So what we have here is a product of sine and cosine, and we've converted that to a sum. Hence the name product to sum identity. Now, if we took the other combinations, we'd end up getting similar formulas. We have 3 more that must have been covered in pre-calculus or in trigonometry. So what are the other identities? It's good to know these identities. So cosine A cosine B would be equal to 1/2 cosine A minus B plus cosine A plus B. By all means, this is what we need to know. We could derive the other identities using these two, but I'd go ahead and write the others also. Sine A sine B is equal to 1/2 cosine A minus B minus cosine A plus B. And lastly, cosine A sine B is 1/2 sine A plus B minus sine A minus B. So all of these identities can be derived using the same process that I used over here. But instead of simply adding the two equations, we can subtract and get the appropriate product identity. So all we have to know is the identities. We don't have to know the derivation as far as this class is concerned. So make sure that you understand the 4 identities and make sure you have it in hand. So going back to sum to product, now in the derivation that I just completed, I had a product and I converted that to a sum. But the goal now is to have a sum and convert it to a product. So to do that, I'm going to consider, sine A cosine B, which should be 1/2 sine A plus B plus sine A minus B. In algebra, you might have learned about substitution, and we are going to use substitution again. So I'm going to let U to be equal to A plus B and V as A minus B. This would imply when I add U and V, I would end up getting A plus B plus A minus B. The B's would go away, so 2A would equal U plus V, which should imply A is U plus V divided by 2. In a similar manner, U minus V would equal A plus B minus A minus B, which would simply be A plus B minus A minus B, plus B. The A's would go away and we would have 2B equals U minus V, which should mean B is U minus V divided by 2. So I'm going to go back and use what I just derived here and plug it in that equation. So on the right hand side I see A, but it turns out that A is U plus V over 2. So I'm going to change that to U plus V over 2. And I'd have cosine U minus V over 2. And that would equal to 1 over 2. I started by saying A plus B is equal to U, and A minus B is V. So I'm going to replace A plus B by U and A minus B by V. I'm going to multiply by 2 on both sides. So the sum here, that's the sum part, turns into a product. So which is why we call it sum to product, and here we have product to sum. So I need to write the other 3 cases, so I will just use the space over here. So in a similar manner, if we have sine u minus sine v, that would simply be equal to 2 times sine u minus v over 2 cosine u plus v over 2, and cosine u minus cosine v would equal to 2 times cosine u plus v over 2 times cosine u minus v over 2. And lastly, that has to be plus, and cosine u minus cosine v would equal negative 2 sine u plus v over 2 and sine u minus v over 2. So there is no need to memorize these. You could just have a note card or a flash card or something, and use it in finding the derivative or integral later on in the course. So if we understand the basics of sine and cosine, we can just extend it to other functions such as secant, cosecant, and cotangent. So what is the secant function? A secant function is denoted as secant of x. This is simply y equals 1 over cosine of x. So since cosine as a period of 2 pi, secant will have a period of 2 pi. The next one is the cosecant function. The cosecant function is defined or denoted as y equals CSC of x, and that is simply y equals 1 over sine of x. Since sine of x has a period of 2 pi, cosecant will have a period of 2 pi as well. And the last case is the cotangent function. It is denoted as COT of x, stands for cotangent, and that is simply y equals 1 over tangent of x. Key things to note here: tangent of x has a period of pi, therefore cotangent of x has a period of pi. The tangent function has vertical asymptotes. This would mean cotangent function also has vertical asymptotes. This is an important remark. Now, when I first started, I had the sine function and the cosine function right there, and neither of them had vertical asymptotes. They are well-defined functions, just like smooth up and down curve, and it's just merrily going about in the rectangular coordinate system. And here I stated that, okay, the tangent function has vertical asymptotes, so the cotangent has vertical asymptotes. But we can't make the same conclusion with cosecant and secant functions. Just because I said that the cosine function doesn't have vertical asymptotes, it doesn't imply that the secant function will not have vertical asymptotes. Why is that so? We know that the cosecant function has sine in the denominator, secant function has cosine in the denominator, and we also know that both sine and cosine become 0 at set points. So that said, both cosecant as well as the secant function will become or will have points where the denominator becomes 0. In other words, it becomes undefined. So there would be vertical asymptotes. So it is important to realize that the secant function and cosecant function will have vertical asymptotes. Before we end here, it's good to know a very important identity or two. These are called double angle identities. These are simply derived from one of these, but I could just write one of them. So let's say sine 2x. The identity is simply 2 times sine x cosine x. Now, how do we know that this particular identity is true? So we know from earlier, sine a plus b is sine a cosine b plus cosine a sine b. I'm simply going to plug in a equals x and b equals x. So that would mean the left-hand side is sine x plus x. The right-hand side is sine x cosine x plus cosine x sine x. X plus x is 2x. So sine 2x would equal sine x cosine x. Well, the two terms are identical, so if you add them together, we have 2 times sine x cosine x, which is sine 2x. So it checks out. So this is one double angle identity that is important. The other one is cosine 2x, and that is equal to cosine squared x minus sine squared x. And we can verify this also. We know from earlier cosine a plus b is cosine a cosine b minus sine a sine b. Plug in a equals x and b equals x. We will have cosine x plus x is equal to cosine x times cosine x minus sine x times sine x. X plus x is 2x. Cosine x times cosine x is cosine squared x. Sine x times sine x is sine squared x. So it checks out. There are multiple ways to rewrite this particular expression with a very simple identity. This is also an important identity. Sine squared x plus cosine squared x is equal to 1. It's quite important. So if I rewrote that, I would have sine squared x to be equal to 1 minus cosine squared x, or cosine squared x equals 1 minus sine squared x. If I take this particular identity and plug it back in here, then cosine 2x can be rewritten as cosine 2x would equal to 1 minus 2 sine squared x. If you plug in 1 minus sine squared x in cosine squared x, it would simplify to 1 minus 2 sine squared x, or two cosine squared x minus 1. Again, you don't have to memorize all of these. As I said, if you know one of the identities, we can derive the other identities. But as far as this class is concerned, you could simply have a note card or a cheat sheet, one of those. So extending the sine squared x plus cosine squared x equals 1 identities, we could come up with other identities involving cotangent and secant and tangent functions. So consider sine squared x plus cosine squared x equal 1. Divide by sine squared x on both sides. So that, the first term would reduce to 1. Now, the second term, I could rewrite it as cosine of x divided by sine of x and square. And on the right hand side, I could write it as squared. So this is a good place to notice something. Sine squared x is sine of x raised to. Same applies for any trigonometric function, may it be cosine, secant, tangent, cotangent. If we have sine squared of x, it simply means sine x, and the entire thing is squared. It's not equal to sine x squared. Do not make that mistake. So sine squared x simply means sine of x, the entire thing squared. So the second identity, or the second statement, is incorrect. So going back to where we stopped, which is right over there, we will have 1 plus. We know what cosine x divided by sine x is. It is simply cotangent x and 1 over sine x is simply cosecant x So the identity here is 1 plus cotangent squared x is equal to cosecant squared x. Now, consider sine squared x plus cosine squared x equals 1. And let us divide by cosine squared x this time. So those two would get cancelled and we'd have 1. And here I could write the first term as sine x divided by cosine x. Entire thing squared. Right hand side I'd have 1 over cosine x squared. We know that sine over cosine is tangent. So we have tangent squared plus 1. We know 1 over cosine of x is secant. Which would give me tangent squared x plus 1 equals secant squared x. I'm just checking something. Bear with me for 1 second. Okay, so those are all the important trigonometric identities. These identities will be needed later on when we take derivatives and such. So You don't have to memorize these, just understand them, and you should be good.